Yes, thank you again to our sponsor for our breakfast and our breaks today, SAIC. We truly appreciate your support. And hopefully everybody's enjoying or has enjoyed their lunch. But to make sure we keep up on time, we're going to get started. And I'd like to invite to the stage right now Coralie Adam. Coralie Adam is the Optical Navigation Group Supervisor at Kinetics, and she is also the Executive Vice President of the AAS Board of Directors. With that, Coralie.
Hello, everybody. Thanks for being here. It's been an amazing symposium so far, and I have the great privilege to introduce our final keynote. But first, I just wanted to make a few remarks. I've been participating in AAS events for the better part of the last 20 years, starting as a freshman at the University of Illinois with the Illinois Space Society. So it's great to see that continued tradition and so many students here asking great questions, here our future, not only in our industry, but in the society. So we encourage you to join us when you graduate and continue to participate, continue to contribute and volunteer as you go far in your careers. But you're not the only future. Everybody in this room is the future of our industry, and we live in it's a very dynamic time, and it's been so wonderful this week to see and hear from so many voices across industry and the public sector and our government partners. Uh, and hearing the diversity of voices, hearing discussions, not only about the current state of things, but the future and where we're headed. And it's just been a breath of fresh air to hear from all these different people. So I thank the planning committee for putting together this amazing group of people to come together and speak. So without further ado, I'd like to introduce our final keynote. Dr. Mark Clampin is the Acting Deputy Associate Administrator in the Science Mission Directorate at NASA headquarters. In this role, he provides executive leadership, overall planning, direction, and management of NASA's $7 billion science portfolio, which is focused on the scientific exploration of Earth, the Sun, solar system, universe, and biological and physical sciences. He brings 35 years of leadership in program and project management, strategic planning, the development of space hardware for astrophysics research. And Dr. Clampin is graduated from the University of London with a Bachelor of Science in Physics and from the University of St. Andrews in Scotland with a PhD in astronomy, not to mention the 35 years in between of all the contributions to Goddard and other institutions. So without further ado, please join me in welcoming Dr. Clampin.
Okay, so good afternoon. It's really great to be here to speak to everybody. And I'm really inspired by the symposium theme here of pathways and partnerships. And I think that's very important for maintaining US leadership in Earth and space science. And I hope you've had a really good week here. As I'm sure you've heard this week, we really have many ways that NASA partners to achieve our scientific objectives. And I'm going to talk about some of those this lunchtime and just highlight some of the stuff that's been going on. So people have been asking me, how are you doing? How's it going? And right now I'm really excited. We've just launched several different missions. We've landed on the moon and all in the space of a couple of weeks for NASA science. And that really sort of keeps us focused and moving forward with our mission. I want to just mention that, we really have these three key science themes, and I think they're important because they provide us with a sense and a source of continuity as we deal with the various challenges that we have going forward. And, obviously the first one is protecting and improving life on Earth and in space, and that embraces Earth science and heliophysics portfolios. The search for life elsewhere really amazingly encompasses all of our science portfolios, and everybody brings a piece the puzzle to that question. And then discovering the secrets of the universe is, my old sort of position before I came to this role, which is, astrophysics. So I want to just start off, it's abundantly clear that science remains at the core of NASA's mission, and that the science we do, really supports the US community in so many different ways. But I wanted just to remind you of the legacy of, space science at NASA, space and earth science, and some of the things we've achieved. And, the very first box at the top left is Explorer 1, which is a mission that, basically discovered the Van Allen belts. Some of our more recent missions have been discovering temporary radiation belts caused by enormous solar storms. We've got, any number of firsts here: the first flyby of outer planets, the first landing on Mars, the first time driving a rover around on a planet outside our own, in our own solar system. And it goes on and on. With the Hubble servicing missions, we really pioneered going to work in space and building things and actually doing real work in space before we did the space station. And JWST is the largest ever space telescope built. It's operating 1 million miles from Earth, and you'll see later producing really great science. So we continue that legacy as we go forward. And at the bottom right there, the lunar landing just a couple of weeks ago, the first ever commercial landing on the moon, with a set of really great experiments that are now delivering science. So science is really the agency's pathfinder. So let me move on now to some of the highlights of what we've been doing, because as I said, we've been doing a lot. And I want to start with an earth science result. And this is really just designed to remind you that everything we do brings value. And a lot of the work we do in earth science, whether it's providing data that's used by Fortune 500 companies or data that's used by our farmers across the West and the Midwest, it all brings value to the US community, both in business and in agriculture. And this is a really good example. Our earth science division has been working on a tool called OpenET, and it's designed to provide farmers and ranchers, in particular in the West, with data on water resources and irrigation. And that's very valuable to them, because if they can optimize how much water they're using, they can make big savings, and that's really valuable for their business. And this OpenET tool is available. They can use it as and when they want, and it provides them with up-to-date earth science observations that help them do their jobs in the most effective way. And of course, it really helps enhance their business. I also want to just say for a second, we're all absolutely devastated by the impact to both our NASA family at JPL, but also our, friends in other academic and nonprofit institutions in California. The wildfires have been absolutely devastating. But I wanted just to highlight one other thing. So during these wildfires, JPL was actually conducting airborne studies of the wildfires, providing both operational data and also data that will help us improve our response for the next fire and the fire after that. So this is an instrument that was flown over Los Angeles while the fires were actually happening, provided a lot of invaluable air pollution data that helped first responders optimize their response, figure out where they could go and where it was going to be really hazardous to operate. And then on top of that, we used all of our other earth science data and resources to provide things like information on infrastructure using our black marble data or nighttime observations of the Earth. So when we have these kind of incidents, NASA really plays a big role in helping the community recover and also helping them deal with the events as they are actually unfolding by supporting first responders. Looking forward, our next big Earth science mission is NISAR, which is a collaboration with the Indian Space Research Organization. This is a synthetic aperture radar mission, and it's going to be able to provide a lot of data on the Earth's ecosystems, plate tectonics, dynamic surfaces, ice masses, and will be a really great addition to the Earth science portfolio. And we're looking forward to seeing that launch in a month or two. Trying to not spend too much time on each chart because we only have a short period of time. Number of people were talking about this result at lunch. This is a picture of some of the data that came back from the OSIRIS-REx mission. And this is just so exciting. And I'm really thrilled by this because I started at Goddard and I was actually managing the science team while they were doing some of the preparations, getting ready to actually do the Bennu tag. So it's really, heartwarming to see this data come back, not only to see these samples come back and provide data, but actually to see them achieve the kind of scientific goals that we set out to achieve with this mission. So, initial analysis of these samples is showing that we found 14 of 20 amino acids used by life on Earth, as well as all 5 nuclear bases that, comprise DNA. So we're not saying we found life here, but if you think of the sort of cooking analogy, we may not have a baked cake in front of us, but we certainly have the cupboard with all the ingredients there. So this is a really big science result for OSIRIS-REx and just shows the value of these missions and just how far they can take us scientifically. So this is a really, really great result. Just last year, we launched Europa Clipper, and just a week ago, Europa Clipper did its first flyby of Mars as it gets ready to do an Earth flyby next year. And eventually, we'll get it out to its final destination, which is Europa. It's designed to try and understand the nature of these icy moons and understand whether there's potential for life elsewhere within our own solar system. So Europa Clipper is a really exciting experiment. Have to be patient to wait for the science results, but when they come, they will be really exciting. So if you're going to work in planetary science, you need to be very patient. The other, and my colleague here called this, wicked cool mission that Planetary Science Division is doing right now is Dragonfly. And, what else can you call it but wicked cool? This is a drone that will fly on a moon of Saturn, Titan, and it's designed to basically fly around the moon, collecting data and then analyzing it to look at the surface of the moon and also analyze the constituents of the atmosphere and really help us understand, again, the possibilities for life on these icy and very different moons that we see orbiting both Jupiter and Saturn. And until we can move further in astrophysics with the next big astrophysics mission, this is where we're focusing our search for life observations. So Dragonfly is really cool. Where else can you fly a drone around another object outside the planet Earth? So really neat stuff. I wanted to just mention what we've been doing over the last couple of weeks. So I mentioned that we have a number of landings on the moon. To the left there, you can see the Firefly lander observing both its own shadow and also the Earth in the distance there. Really amazing. It has 10 experiments which have all been returning data. We also have IM2. IM2 unfortunately tipped over, but we were still able to collect lots of really valuable science data and operate some of the science instruments. And again, I want to emphasize, the goal here is to enable sort of commercial lunar capability. And this was one of the higher risk rewards attempts to land because it was in an area at the South Pole, which we know is very gnarly in terms of craters and the surface of the moon in that area. So we still got really great data, and we're still moving forward with the next CLIPS program. And we think this whole idea of doing these high risk return experiments is working out very well. I'll just mention Lunar Trailblazer. Unfortunately, we're still trying to regain contact with this mission. The goal of this mission was to do spectrometry of the moon, look for minerals. We're hoping we can perhaps recover it if we can get communications with this. So JPL are working very hard to try and restore communications right now. Biological and physical sciences is also moving forward. This is a really neat result. We were recently able to fly Dr. Rob Firl, who became our first NASA-funded researcher, to take his own experiment into space. And he's been studying how plant genetics change or evolve into microgravity environments. So you can see here he flew on Blue Origin's NS-22, and he's actually holding the experiment there. And in the middle, you can see one of his postdocs actually preparing that experiment. So this is, a new way of doing science that takes us beyond what we've been doing on the station over the last 2 decades and prepares us for this next era of working in space with all of these new commercial launch capabilities, both now and in the future. So we're really excited about what we can do in both studying biology and supporting the manned spaceflight program, and also do other experiments, hopefully in the future, that will inform some of the other areas that we're interested in quantum physics. So this is really great result. My boss would kill me if I didn't show a chart of Parker's solar probe, her pet mission. Parker's just an amazing mission, and I was reading my notes here before giving the talk, and it dawned on me that we seem to be making a habit in NASA of having big events right around the end of the year during the holidays. We started with James Webb launching on Christmas Day, and Parker Solar Probe on Christmas Eve made its closest flyby of the sun. And I'm just going to read the data here because it just makes my head hurt. So it broke its previous record by flying just 3.8 million miles above the surface of the sun. And it's now the fastest human-made object that's ever existed, flying at 430,000 miles per hour. So that's pretty amazing. And it really is getting into the region now where it can start to help us understand what's going on inside the corona of the sun, and help us understand how these space weather events form and then evolve. And I wanted to, we had a panel here spending some really useful time talking about space weather and, the various aspects. But one thing I want to really emphasize is we do a lot of heliophysics at NASA, and it's really focused on the research aspect rather than the operational. So we do a lot of research and the fly missions that inform us and help us understand the nature of the sun and how these events form, evolve, and really understand what's going on inside them, because you need to understand the physics in order to have a great operational program that's going to give you useful data. So we see our role as really providing the research and the understanding of the physics that then informs our ability to have an operational program that gives us meaningful data and really does help us protect our planet. I said at the beginning, we've been launching a lot of stuff. So a week after I left Vandenberg, we launched this mission, which is called EASY, the Electrojet Zeeman Imaging Explorer. And this is actually a constellation of 3 satellites. I'm not going to spend too much time talking about this one because I want to get on to the other one that we just launched for heliophysics. This is PUNCH, the polarimeter to unify the corona and heliosphere. And the basic idea of this mission, which is a constellation of 4 satellites, is to do coronagraphic imaging and polarimetry to really help understand the 3D structure of events as they occur on the sun's surface and out into space. So it's really trying to help us understand how solar corona and events, CMEs, evolve towards the solar wind. And again, that comes back to this point that we're trying to understand the physics of how these events form, evolve, and then understand the implications from what we see so that we can inform the operational aspect of space weather. Punch was a really nice experiment because we launched it as a rideshare. So Punch launched with SphereX, which I'll talk about in a minute. And this was our first real rideshare experiment for the Science Mission Directorate. So we got to launch 2 missions for the price of 1. You get twice the science for the price of 1 launch. And it worked really, really well. So we were able to deploy all 4 of these satellites after we'd launched the mission. And then we also deployed SphereX. And so this is SphereX, which is the weirdest looking satellite you've probably ever seen. Looks like a big trumpet. It's basically an infrared hyperspectral imager to do astrophysics. And the way it works is that it's a low Earth orbit mission and is doing near infrared spectroscopy. And the way it does that, rather than using grisms or prisms, it actually uses a series of color filters. So it really is a hyperspectral imager, but it has a lot more bands than you would see, for instance, on an Earth science mission. And the basic idea here is to do an all-sky survey. So this is why we build explorers. They give us a science goal, and we work with the PI. The PI launches the mission, achieves their science goal, but these missions then produce this rich legacy that we can open up to the whole community, and the community will find great things to do with these missions. And I'll give you another example. TESS was an explorer that was designed to study exoplanets. In fact, it was designed to find small rocky planets that could be studied by JWST. If you look at what TESS is doing now, 60% of the science it's doing is looking for transient events. So the community have figured out how to use these missions in ways that that even the PI didn't think of when they conceived and launched it. And we expect the same from this mission. So this mission is designed to help inform us on the very first moments of the Big Bang, this period that's called inflation. It's also designed to study ices in star-forming regions and help us understand how the materials in star-forming regions ultimately end up in protoplanetary systems, and then how that ultimately ends up as life. So it's got some very laudable goals there, but as I said, it will do more. These missions really do earn their money. And I'm going to finish up, before I take questions, by just showing you a couple of JWST results. And this is a mission I worked on for a long time, so I'm always thrilled to show JWST results. And this one I think is really neat. So on the left, generally we expect to see these really beautiful images. But the reason we built JWST was to find what was going on in the very early phases of the universe. What was happening in the first billion years after the Big Bang, and in particular that period when the very first stars formed, and then how they evolved and became galaxies. And one of the really neat things that JWST is finding is that we really don't understand at some level how that process works, even though we thought we did when we launched it. So we are seeing a lot of very massive galaxies that formed extremely quickly after the Big Bang. And this is raising questions about how could that happen? How do you get this much mass into a galaxy so quickly? And one of the possible keys to answering that question are the things you see on the left. Now, they're not very photogenic, and astronomers have called them little red dots. But what they are is extremely red objects. And when we use the spectroscopic capabilities of JWST, we find that there's very strong evidence that these are supermassive black holes that have formed extremely quickly. And so this may be a clue to how you get so much mass into these galaxies so quickly. So stay tuned. Now, little red dots, you're going to hear more and more about them as we start to really understand what happened in the first billion years of the universe, as JW continues to study that part of the evolution of galaxies. On the left is a protoplanetary disk that was taken by James Webb Space Telescope. This object was made famous 25 years ago when the Hubble Space Telescope observed it in the optical. And what you're seeing here is an edge on disk. So you see that sort of dark section going through the middle, and on top and the bottom, you're seeing this disk edge on. And because it's very young and there's a lot of physics going on inside this disk, it also has a jet and is spitting out material, basically because of the magnetic fields caused by all this material that's fallen onto a disk as the star starts to form. So this is really telling us a lot about how stars form, and also how protoplanetary systems and ultimately planets form as a part of that process of star formation. And this is a really pretty image, but if you're an astrophysicist, it's really interesting, because when we look at this and break it back into its individual colors, we can actually see different layers of dust and different kinds of dust at different places in this disk, which is telling us about what happens as this disk evolves and how material is moved around as they evolve. So I'm going to finish there and just finish up again by saying, you know, we have a really strong focus on our science in the Science Mission Directorate. We believe all of our missions really inform the science that we do and the research that's done with the data that comes from these missions. And we will continue to focus on our mission. Thank you. I'm sorry, and I thought they hadn't added this in, but they did. So let me just say real quickly, going forward, astrophysics is looking at two missions. On the right, you see the Roman Space Telescope. And Roman is a mission that's designed to do a very large survey that will try to help us understand the nature of dark energy and dark matter. And I'll just remind you that Hubble kind of shares a piece of a Nobel Prize for being in at the beginning when dark energy was discovered. So this is really sort of Hubble handing over the challenge to the Roman Space Telescope, and Roman will help us try and understand what dark energy is by really nailing down the cosmic distance scale all the way back to the early universe. And then on the left is the next big flagship for NASA astrophysics, which is the Habitable Worlds Observatory. And that mission is designed to image nearby stars and search for small habitable planets. And when we find them, it can then characterize their atmospheres to look for evidence of life. So apologies, I didn't realize that one had been added back in. So there's a bonus. Okay, questions? Okay.
Thank you. Great. Thank you so much for the whole presentation. Dr. Clampin, as you think, as we as a community think forward to being able to benefit from all of the great data that is coming from all of these observatories and instruments, can you speak a little bit about NASA's plans for being able to optimize the use of that data and making, converting it into products that are of significant use and value across the space enterprise?
So let me start by just talking about Earth science. One of the real goals over the last couple of years in the Earth Science Division has been to try to make the data not only accessible via cloud storage and open access, open science, but also trying to find ways by working with the various communities that use their science data to make it more accessible. And the one I showed you, OpenET, is a great example of how, by going to meetings like the Commodity Classic and talking to the guys who are sort of, driving across fields in tractors, how can we help you? What would work for you so that you can make the best use of our data and optimize, what you're doing in terms of irrigation or when to plow or, health of your crops. So we've been spending a lot of time in Earth Science doing that over the last 4 or 5 years. As far as some of the other divisions, every division has a different sort of community that works with it. And I'll give you one other example, for instance, with astrophysics. The Roman Space Telescope is going to really change the paradigm for how we do science with a telescope like Roman. So the current model has always been that with Hubble, Chandra, James Webb, if you're a scientist, you write a proposal, you do a really good job, and you've got a really great idea, the peer review panel might award you time, and then you can just download your data from the archive when it's available, once the observation's been done. With Roman, we can't do that. It's a survey. It's the first ever astrophysics survey mission that we've done in astrophysics at the flagship level. So we've basically focused on community-driven surveys. So we can't do a million different surveys because that then sort of negates the reason for doing surveys. So we've really worked with the community to identify 3 or 4 major surveys that we will do. That data will go into a cloud, and because there's so much of it, we're working to provide the user community with cloud computing so that we're not just enabling the people who have immediate access to a supercomputer, but enabling our whole astrophysics community to be able to work with the data. And I'll just say, we're starting to hit the sort of cusp with James Webb, where some of these deep field programs are so big that people are actually having to process the data on supercomputers, because you have this enormous amount of data, and then you want to go through and look for all those little red dots. That takes a lot of computing power. And if you're trying to use AI, ML methods, you also need optimized computing to help you do that. So we're constantly thinking about not just the missions, but how we make sure we get value from the missions by optimizing how we provide the data to the community, whatever that community might be.
Thank you, Dr. Clampin. Personal question. What 1 or 2 scientific discoveries would you like to see happen during your NASA career, and inspire these young folks up here to carry the torch forward, trying to get that done?
So I'm probably leading the jury here, but I think one of the things that I would really like to see is what I would call legacy observation with Webb. Now, some of you may know the Hubble Deep Field was a program undertaken with the Hubble Space Telescope, and the then director Bob Williams decided he was going to just put 300 orbits, which was really a lot at the time, into this one program, and that program pretty much changed how we think about the early universe. And I think, as we look at what Webb has done up to now, and we're starting to understand where the sort of key scientific challenges are and what Webb can really do when we push it to the limit, that it's time to start thinking about a legacy observation. And that could be a super deep field. It might be a very long exposure on the atmosphere of an exoplanet. I think the science community need to decide that. And I have to say, the other one for me will be getting the first exoplanet that potentially has evidence of life with habitable worlds.
Thanks, Mark. Yeah, so, one of the themes of this symposium is about U.S. leadership.
Yes.
And so we have all these amazing scientific contributions from NASA and partners. And how do we do a better job quantifying and documenting the impact of our science, not only on the economy, but on the U.S. innovation ecosystem in general?
That's a really good question. It's actually something we've started thinking about very seriously in the Science Mission Directorate. Now, NASA has in the past done economic impact studies, and that's a really good place to start. I think you can also look at, if you're just looking at the science, you can just look at things like impact, scientific impact in major fields and get a very quick assessment of the impact that our missions have. I think capturing the impact on the commercial world is harder to do. And that's something we've really started trying to think about, because soon as you start thinking about any of these missions, and I gave a talk last year on web and was pointing out a lot of the everyone's in this talks holding their phone up taking pictures, and pointed out to them all the early investment in charge coupled devices was done for the Hubble Space Telescope first generation instruments. And actually that subsequently won a Nobel Prize for the two inventors of the CCD. But at the time that Hubble was getting ready to fly, and the then AA decided that he really didn't want to fly television cameras on a telescope that was really supposed to be a major breakthrough, and kudos for doing that. That's one example. You can look at any of our missions. Every single mission we do, we are pushing the envelope on technology. And if you're pushing the envelope on technology, you are producing all sorts of spin-offs or enabling new capabilities that we haven't had before. And some of those we never even really appreciate, like on web. Just the simple matter of not wanting to build a massive isolated table to do testing on led us to work with industry to come up with a camera that would allow us to measure down to picometers. And we are measuring mirror surfaces to picometers in rooms like this. And that subsequently was used by that company, in LASIK, in the LASIK business. If you've had LASIK surgery, they use a lot of techniques that they use to do web mirrors to measure your eye. So it's easy to do when you start talking about individual cases. It's very hard to do when you sort of try to look at it as a collective. But again, even with our SEO missions, we're working with US industry to enable a new sort of lunar economy. And these things take time, but we're making great progress. Thank you very much. Sure.